Let's take a look now at section 4.5 about exponential and logarithmic equations. Now, when we're solving exponential and logarithmic equations, a lot of the same techniques are going to work because, of course, these two types of functions are related. When we look at exponential functions, we can set exponential functions equal to a constant or to another expression and end up with an exponential equation. Now, exponential equations can be solved a few different ways depending on how they start out. So, for example, the nicest case of any exponential equation is whenever you have two expressions set equal to each other that have the same base. So, for example, if I have 2 raised to the power 3x plus 5 is equal to 2 to the power 2x minus 4, this is the simplest possible case. Because remember, exponential functions and logarithmic functions are inverses of each other. And you say, yeah, so? Well, that means that an exponential function has an inverse. Yeah, so? Well, as we saw in a previous section, a function has an inverse if and only if it's 1-to-1. So here, we can use that 1-to-1 property a different way. The 1-to-1 property says if I have my y values equal, that must mean my x values are equal. In this particular case, what that means is if these two are equal to each other, that must mean that our arguments are equal to each other. So here you can think of this as 3x plus 5 equals 2x minus 4, right? If 2 to a power is equal to 2 to a different power, because an exponential is a 1-to-1 function, that means that those two powers must be the same. Oh, but now that's not really an exponential equation. This is just a nice, simple linear equation, and that can be solved without any problem. Because after all, I can now subtract 2x from both sides, and that's gone. And that'll leave me x plus 5 equals to negative 4. And now I can subtract the 5 away, and we get a result. Subtract 5 away, and we get a result. And there we go. We could even plug that in if we wanted and check that out. Plug negative 9 in here. Negative 9 times 3 is negative 27. Negative 27 plus 5 is negative 22. So here I could even check this. And I would get 2 to the, what did we say, negative 22 is equal to, and if I plug it in here, negative 9 times 2 is negative 18, minus 4 is also negative 22. And sure enough, those two are equal to each other. 2 to the negative 22 is equal to 2 to the negative 22. This works as long as the bases are the same. All right, so for example, I might take 7 to the power 5x minus 9 is equal to 7 to the power 3x plus 1. Pause the video and go ahead and give this a try. Once you're ready, go ahead and unpause and we'll go through it together. All right, so this one works the same as the previous one. Looking at this, we note that you have the same base, and because an exponential function is a 1-to-1 function, if 7 to this power equals to 7 to that power, that must mean that this first power is the same as this second power. Oh, but now that's not exponential anymore. Just a nice, simple linear equation. So I could subtract the 3x from both sides, and that would give me 2x minus 9 equals to 1. After all these are gone now. And I could add 9 to both sides, and that would give me 2x equals to 10. Getting ahead of myself there. And finally, I can divide both sides by 2. Divide both sides by 2. And that gets me an answer of x equals to 5. And I could even check that if I want to, right? I can check this. And I can get, well, let's see here. 5 times 5 is 25. 25 minus 9, well, that'll give me 16. So that's 7 to the 16 power equals, let's see here, 5 times 3 is 15, plus 1 more is 16. So the left side and the right side are the same. So yeah, that works out. We can check our equations. We can check our solutions by plugging them into our equations, and those work out quite nicely. Normally I'd flip to another page, but we've got plenty of room here, so let's look at a few more examples. Let's consider an example now that looks like this. We'll take, let's say 2 to the power 5x minus 3 is equal to 8 to the power 2x plus 1. Now at this point you say, well, okay, now that's different. Because over here we had the same base on both sides of the equal sign. Same thing here. Here we don't. Well, sure we do. I say, no, we don't. Look, that's a 2 and that's an 8. Those are not the same base. Well, they're not, except they are. Wait, what? This is a video lecture. We can't give you a frowning face to show you that we're confused. Well, okay. 2 and 8. They may not look like they have the same base, but they do. Because after all, here, recall that 8 is nothing more than 2 to the third power. So even though 8 and 2 have a different base, well, they really don't, because I can write 8 as a power of the number 2. So here what I'm going to do is I'm going to leave this one alone. I'm going to leave this as 2 to the power 5x minus 3 is equal to, instead of writing that as 8, I'm going to write that as 2 to the third. And now instead of saying I'm raising 8 to this power, I'm going to raise 2 to the third to this power. Oh, but look, I have something that has a power and is being raised to another power. Well, those two are going to get multiplied together. Whenever you raise something to a power and then raise that to another power, the two powers multiply together. So this will give us 2 to the 5x minus 3 is equal to 2 to the 6x plus 3. And now that looks just like one of these. So here, even though they don't have the same base, you can rewrite it so they do have the same base. And once you rewrite it this way, things are as nice as they were over here. Because now I can say, well, look, 2 to a power is equal to 2 to a different power. So now I can just write those powers as being equal to each other. So I can write this as 5x minus 3 equals 6x plus 3. And now we can solve. Let's go ahead and let me subtract 5x from both sides. I like to pick on the smaller x, make that go away. And that's now negative 3 equals 6x minus 5x. Well, that's just going to be 1x, isn't it? It's just going to be 1x plus 3. And now I can go ahead and subtract the 3 over this way. So minus 3 and minus 3, and that's gone. And that'll leave me negative 6 is equal to x. And that's my solution. All right? So now I can even check this if I need to. Here I can check this as, well, let's see. Negative 6 times 5 is negative 30. Negative 30 minus 3 is negative 33. Over here, negative 6 times 2 is negative 12. Negative 12 plus 1 is negative 11. Oh, but 8 can be written as 2 to the power 3. So here I can write this as 2 to the negative 33 is equal to 2 to the third to the negative 11. After all, that 8 becomes 2 to the third. And sure enough, that does give me the same thing on both sides. 2 to the negative 33 is equal to 2 to the negative 33. So you can even check that out, and yeah, it works out quite nicely. If ever you're not certain that you've done something correctly, well, plug it in. If this is a solution, you should be able to plug it in and make both sides equal. In some cases, you won't even have a power on one of these, and that's okay. Because after all, if something doesn't have a power, well then, automatically that means its power is 1. So for example, I might have 7 to the power 12x minus 3 is equal to, let's say 1 over 49. Okay. Now, we can take these, and even though they don't have the same base, we can write them in the same base. All right. You notice this doesn't have a power. That's fine. If something doesn't have a power, that just means it's power 1. Just like that. Okay. Now, I can write 1 over 49 as a power of 7. After all, 7 squared is 49. So to reciprocate it, I can use a negative second power. All right? 7 squared is equal to 49, which means 7 to the minus second power is 1 over 49. That's what the negative does. It reciprocates your result. So here we can write this as 7 to the power 12x minus 3 is equal to 7 to the minus second to the power 1. Now, of course, here that's, well, that doesn't change anything. Anything to the power 1 stays itself. So here, let me just not write the power 1. I have 7 to the power 12x minus 3 is equal to 7 to the power minus 2. And now we're back in our previous examples, where as long as the bases are the same, you can just look at the exponents. That's the one-to-one property of an exponential equation. So now that just tells us that 12x minus 3 is equal to negative 2. And now things are nice. Because here we can go ahead and add 3 to the other side. And that's going to give us 12x, that's gone, is equal to 1. And now we can divide both sides by 12, and that gets us our result. So we have x is equal to 1/12. And there we go. And we can even check this. All right, if I plug in 1/12 here, 1/12 times 12, well, that's 1. Let's write that out. Here, that's 7 times, raised to the power 12 times 1/12 minus 3. Well, let's see here. 12 times 1/12. Well, that's just the number 1. The number 1 minus the number 3, that's negative 2. So here that's equal to 7 to the negative 2, which is 1 over 49, which that's what we wanted. So that does work out as a solution. Right? Again, if you're ever not sure if you've done this correctly, you can go ahead and check that out, plug it into the equation, and we get our result. Now, there are going to be some times where that's not going to work out quite as nicely. Notice that in every one of these cases, either we started with things that had the same base, or with a little bit of effort, we could write things so that they did have the same base, even if they didn't start off that way. Same thing we had here. But there are going to be some cases where you can't write things in the same base, at least not easily. So for example, let's say I have 2 to the power 3x minus 5 is equal to 3 to the power x plus 4. Well, now those aren't in the same base, nor do I really know how to put them in the same base. After all, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 3 to the power 1 is 3, 3 to the power 2 is 9. Yeah, I can't write one of these in terms of the other one. Okay, so if I can't do that, what should I do? Well, remember, exponentials have other properties besides being a one-to-one operation. Another property of a logarithm, I keep saying logarithm because I'm getting ahead of myself. Another property of an exponential function is that its logarithm is an inverse. So at this point, we could now take a logarithm of both sides. Now remember, this is an equation. Whatever you do to one side, you got to do to the other. So that leads us to a little bit of a problem, though. If I use log base 2, oh, that'll make this go away. That's nice. Oh, but log base 2 doesn't make this go away. Right? They'd have to be the same base to be inverses. Okay, so this would go away, but this would now be harder because now that's not just an exponential, it's an exponential inside of a logarithm. And that just doesn't seem nice. We can go the other way around too. We can take log base 3 of both sides. That makes this easier, but now you have a logarithm with an exponential over here. There are ways of working around that. However, rather than to guess which one we should do, and it actually would work out if we did it that way. There are ways of cleaning that up significantly. But to keep things a little bit smoother, we're going to use a single logarithm each time. And that logarithm will be the natural logarithm. Technically, we could use any logarithm we like. But by using the natural logarithm, one, we're going to get something that is predictable. We'll know what to do each time. There's no guesswork, and there's no chance of, maybe I should do something else. But also, if you get some unpleasant numbers, it's a little bit simpler to clean those up. So here's how this is going to look. I'm going to take both sides of my equation, and I'm going to take the natural log of both sides. Again, any logarithm would work, but I'm going to show you guys using the natural logarithm. I'm going to take the natural logarithm here, and again, whatever I do to one side, I'm going to do to the other side, just like that. So now what I want to do is I want to take advantage of one of our properties of the natural logarithm. In fact, every logarithm had this property. So here, recall, whenever you have, and here I'm going to write it for the natural log, although this would be true for any logarithm, recall that if you have the natural log of something to a power, that's the same as taking this power and multiplying it times the natural log of just the a. So that power can be brought to the front as a multiplication, as a product. So we're going to take advantage of that property here because, hey, look, I have something to a power inside of a logarithm. I have something to a power inside of a logarithm. That power can be brought out. So now I can take this and bring it out, and I can write this now as 3x minus 5, and I'm going to put that in parentheses for reasons that will be apparent in just a moment. And then now that's being multiplied by the natural log of the number 2. Just like over here. That power came to the front times the natural log of the original base, which was the number 2. I'm going to do the same thing on the other side. Here, take this, x plus 4. That power now becomes a factor. And now you're going to multiply by the natural log of your base, by the natural log of 3. Now that might look messy, but this is a linear equation. You say, well, yeah, okay, those look linear, but what about those? Those are not nice. Those are just numbers. The natural log of 3 is a number. It's about 0.9. The natural log of 3 is a number. It's about 1.1, something like that. You say, oh, so we need a calculator. All right, we need to know what those decimals are. We need to know what those numbers are. No, not at all. We use these numbers just like any other number. Because after all, here, let's go and do this off to the side. Recall how multiplication works. If I have 3x minus 5 times a number, let's say, for example, I had times the number 7, what I would do is I would distribute. I would say 3x times 7, and then separately I would say minus 5 times 7. So this would be 3 times 7x minus 5 times 7. And of course I would clean that up, and that will give me 21x minus 35. I can do the same thing here. After all, that's just a number. So I can distribute it. I can multiply there and there. And same thing for this one. That's just a number. I can multiply there and there. Okay, so let's multiply. Okay, well, when you multiply something like this, you multiply the two constants, and then you just leave the x alone. All right, well, that's what I'm doing here. I'm going to multiply the 3 times the natural log of 2. Now, normally, if you multiply two numbers, you just get a different number, right? 3 times 7 makes 21. Over here, that's not a nice number that we know. We don't exactly know how to express the natural log of 2 other than to write the natural log of 2. So we're just going to leave it like that. 3 times the natural log of 2, we're going to write as 3 natural log of 2. Times your x, don't forget your variable right there, minus 5 times the natural log of 2. Well, the best we can do is write that as 5 natural log of 2. If we do that on the other side, we get pretty much the same thing. Natural log of 3 times x is natural log of 3x. I would suggest you put these numbers after the logarithm in parentheses, because otherwise it's going to look like you're saying natural log of 2x. It's going to look like these two go together, but they don't. It's the natural log of 2 and then separately times x. The parentheses are good notation. It's a good way to make sure you don't confuse yourself later on what goes together. Same thing here. That's the natural log of 3 and then separately times x, not the natural log of all of this. So be mindful of your notation. It is important to help keep you straight as you look at some less than nice looking numbers. Here, 4 times natural log of 3 is 4 natural log of 3, just like that. And now, as unpleasant as that might look, that's a linear equation. Look, it's number x minus number equals number x plus number. That's just like what you have over here. Number x plus number equals number x minus number. The numbers might look a little less pleasant, but it's still a linear equation. Everything's power 1. So how do we solve a linear equation? Well, just like we always do. We want all the x's on one side. We want all the other numbers on the other side. So let's do that. Here, these both have an x in common. So all the things that have an x, let me go ahead and bring them this way. These don't have x's. So whatever doesn't have an x, let me move it to the other side. And let me do that all one step at a time. If I subtract the natural log of 3x here, and I subtract the natural log of 3x here, these go away. And now I have 3 natural log of 2x minus natural log of 3x. I'll be able to simplify that in a minute, but for now I'm just going to write it down like that, one step at a time. That 5 natural log of 2 is still there. And now on the other side of my equal sign, all I have is 4 natural log of 3. So now let's get rid of this part. After all, I want all my x's together. It doesn't have an x, so let's move that over there. That's going to be plus 5 natural log of 2 plus 5 natural log of 2. That goes away. And now I have 3 natural log of 2x minus natural log of 3x equals 4 natural log of 3 plus 5 natural log of 2. We're almost done. Look, all my x's are together. Notice that x is a common factor of these two terms. Because it's a common factor, we can factor it out now. So we can write this as x times, well, if we factor out an x from here, we're just left with 3 natural log of 2, minus, if we factor an x out of here, we're just left with the natural log of 3. Is equal to all of this stuff, 4 natural log of 3 plus 5 natural log of 2. And finally, you have x times a number. Now, as unpleasant as that looks, that's just the number. Notice there's no variables in there. So if I want to get that x by itself, these are being multiplied. To get rid of a multiplication, I divide. So what I'm going to do now is I'm going to divide both sides by the number I'm trying to get rid of. It's a big, unpleasant looking number, but it's still just a number. So that's 3 natural log of 2 minus the natural log of 3. 3 natural log of 2 minus the natural log of 3. These now go away, and that's our result. So in the end, we get that x is equal to 4 natural log of 3 plus 5 natural log of 2 over 3 natural log of 2 minus the natural log of 3. Ain't that a funny looking number? There are further ways of simplifying this. Remember, we do have ways of combining numbers. We have properties of logarithms here. We could take this and treat it as a power. We could take the 5 and treat it as a power on the 2. Same thing here. We can treat that as a power and that as a power. And then since we have the sums and differences of logarithms, we could then combine those. And then since we have a quotient of logarithms, we could use the change of base theorem to squeeze it all together. We're not going to be doing that. So long as you can express your answer this way, that'll be sufficient. Can this be simplified? Absolutely. But we're not going to worry about going any further than this. All right? So let's take a look at another example of that. All right. Example, let's go ahead and take, let's see. Let's do 5 to the power x minus 4 is equal to 3 to the power 2x minus 5. Let's make that a plus 5. All right. So go ahead and give this a try. Pause the video. There won't be anything different about this problem than the one you just saw. So go through it, use the previous one as a model, and once you get to a point where you feel like you've gotten an answer, go ahead and unpause the video and we'll go through it together. All right, so let's see here. I'm going to take the natural log of both sides. So that'll give us the natural log of 5 to the power x minus 4 equals the natural log of 3 to the power 2x plus 5. We can now take these powers and bring them out. So this will be x minus 4 times the natural log of just the number 5 is equal to 2x plus 5 times the natural log of just the base 3. But these are just numbers. We can distribute these. Multiply there, there, and multiply there, and there. So now we can have natural log of 5 times x minus 4 natural log of 5 equals 2 times natural log of 3, don't forget your x, 2 natural log of 3x, plus 5 times the natural log of 3. And we're distributing. Now, all the things that have x's, we want them together. Whatever doesn't have an x, we want those on the other side. So here, let me subtract 2 natural log of 3x so that it's over here now. That's gone. And since all my x's are together, let me go ahead and move this one over to the other side. So let me say plus 4 natural log of 5. And same thing over here, plus 4 natural log of 5. Whatever you do to one side, you have to do the same on the other. Those are gone. And now we're left with the natural log of 5x minus 2 natural log of 3x. These two are the only ones left on this side. That's gone. Over here, these are gone. And the only thing left on this side would be 5 natural log of 3 plus 4 natural log of 5. Just like that. Notice now you have a common factor of x, which you can factor out. That is x natural log of 5 minus 2 natural log of 3. You factor out an x from each of those. That leaves you just the natural log of 5 minus 2 natural log of 3. Over here, there is no x, so there's nothing to worry about. All of our x's were over here. And now, that's x times the number. We don't want x times the number. We just want the x. Okay, so divide to get rid of the multiplication. I'm going to divide both sides by the natural log of 5 minus 2 natural log of 3. So that is now gone, and we're left with our result. X is equal to 5 natural log of 3 plus 4 natural log of 5 over natural log of 5 minus double the natural log of 3. Just like that. Finally, for exponential equations, we saw previously that not every instance of an exponential equation had to have variables on both sides. Most of them do, but we also saw a few examples where you just have a number on one side. The variables are over here, but there's nothing at all over here. Now, in all of the instances that we saw before, we had either things that had the same base or that could be written in the same base. But now, what happens if I have two things that cannot be written in the same base, and one of them has a variable, but the other one doesn't? Well, it's actually not too much. It's actually a little bit simpler than this. So that'll be our last example. So here, let's see what happens if, instead of having 5 to the power x minus 4 equals to 3 to the power 2x plus 5, let's just say that I didn't have any variables. Let's just say it was 5 to the power x minus 4 equals 3, and that's it, just 3. Okay, well, now one thing we could do here is write them in the same base. No, we can't. 3 to the power 1 is 3, 3 to the power 2 is 9, 3 to the power 3 is 27. Yeah, I can't find a nice way of writing these with the same base. So what I want to do is I want to use a logarithm to simplify this out. You say, well, okay, we'll use the natural logarithm. After all, that worked out in the last two examples. And, of course, we could do that. We can use the natural logarithm to solve this. However, whenever your exponential equation has only variables on one side, although the natural logarithm is useful, it's a little more convenient to do the following. Instead of using the natural logarithm, we're going to use the logarithm of the base of the side that has the variables. Or in other words, instead of taking the natural logarithm of both sides, I note, okay, only this side has a variable. Its base is 5, so let me use log base 5 instead of the natural log. Notice right here, that's just a number. I started off with the number 3, I took the log base 5 of the number 3, and I don't know what that is. It's just a number. Well, that's fine. We'll just write it down the same way. We'll write it as log base 5 of 3. One thing to note is that this doesn't need to be simplified. Numbers don't need to be written as a decimal or a fraction. All right? This is a perfectly good way of expressing a number. Just like if I say I'm going to take the square root of the number 7. Well, I could try to find it as a decimal, but that decimal is just an approximation. It's not completely correct either. So why not just leave it as the square root of 7? Same thing here, log base 5 of 3. Well, even if I were to plug this into a calculator or a computer and get a big decimal, it's still not correct. It's only an approximation. So why not just leave it like that? The important thing to notice is on this side, because recall that the logarithm and the exponential are inverses as long as they have the same base. Or in other words, if you have log base b, recall, as long as you have log base b of b to a power, you're just left with that power. Well, log base 5 of 5 to a power will leave me just that power. And now we're just about done. Because notice, here the x is almost by itself anyway. All I have to do is get rid of that 4. So let me go ahead and add 4 to both sides. Let me add 4 to both sides. And we're done. That's going to give me x equals. Here you can write it one of two ways. You can write log base 5 of 3 plus 4. Or you can write the 4 first. 4 plus log base 5 of 3. After all, it's addition. Addition is commutative. You can add in, you can put it in whatever order you like. The reason I suggest you write it this way instead of the other way, I have seen some people will write log base 5 of 3 plus 4, and then the next thing they'll do is they'll combine these and say, oh, that's equal to the log base 5 of 7. Log base 5 of 7, which is not true. You don't want to do this. This is not true. Because 3 is the argument of a logarithm. 4 is not the argument of a logarithm. It's just a constant. Are there ways of combining this? Maybe, but that's definitely not the right way to do it. So here my suggestion is you write the constant first to keep you from making this mistake. So that's our answer. Notice that it is quite a bit shorter than the previous one. Yeah? So if you have two bases that are different, if both have a variable, it's going to be long. There's not really a way around that. But if only one side has a variable, you can make it a lot shorter by using the logarithm of the base of the side that has the variable. So let's see that again. Let's go ahead and try, let's say 7 to the power 3x minus 8 is equal to 2. So in fact, you give that a try, pause the video, and when you get to an answer, go ahead and unpause and we'll go through it together. All right, so let's take a look here. The two bases are different. I can't write them with the same base, but that's okay. There's only one side that has a variable, so I'm going to use a logarithm that uses this base, the number 7, as its base. So I'm going to write this as log base 7 of 7 to the 3x minus 8 is equal to log base 7 of just the number 2. Here, log base 7 of 7 to a power leaves me just that power. On the other side, log base 7 of the number 2, well, that's a number. which we're just going to leave as is. Okay. Now we're almost done. Here, let's go ahead and get rid of that minus 8. I can do that by adding 8 to both sides. So that's going to be plus 8 there and plus 8 there. That's gone. And I can now write this as 3x. The 8's are gone. Here, I'm going to write the 8 plus the log base 7 of the number 2. And finally, divide by 3. You might say, well, how do I divide that by 3? Oh, it's easy. You go divide by 3. And that's it. You're done. Here, if something can be reduced, you can, but that's not generally going to be the case. Here, we're just going to write this as 8 plus log base 7 of 2 over 3. Some people prefer to separate this. Some people will write this as 8 over 3 plus log base 7 of 2 over 3. That is also correct. Either of these is acceptable. Either of these is a good answer. All right. So that's our solution. So now let's take a look at the other kind of equation that we have in this section, and that's the logarithmic equation. Just like with our exponential equations, if you have a equation that has an exponential expression on both sides with the same base, the one-to-one property allows you to just look at the powers set equal to each other. The same thing will happen here. If you have your logarithmic equations, if they have the same base, well, let's see here, that's going to be log, and here I'll just pick an arbitrary base. Let's say log base 3. If I have log base 3 of 5x minus 4 is equal to log base 3 of, let's say, 2x plus 7, well then the one-to-one property still applies. So if I have log base 3 of this equals log base 3 of that, well then this must equal to that. So that's going to give me 5x minus 4 equals 2x plus 7, just like that. But now we can go ahead and solve this equation because it's just a nice, simple linear equation. If we subtract 2x from both sides, that part's gone, and that'll leave me 3x minus 4 equals 7. I can go ahead and add 4 to both sides. That's gone. And that leaves me 3x equals to 11. And finally, I can go ahead and divide on both sides by the number 3. And that'll get me my result. X is equal to 11/3. Just like that. Now here, we actually have a little bit more to do. And you say, what else could we do? We have our answer, right? X is equal to 11/3. Well, we have to check our answer. And you say, oh, well, okay, we check our answer to make sure we did it right. Yeah, make sure we didn't make any mistakes. Well, that's not quite what I mean. Go ahead and remember, let's go ahead and recall the graphs of the exponential and the logarithmic parent functions. If you have f of x equals a to the x, your graph looks like one of these two. It either looks like exponential growth or it looks like exponential decay. And it depends on whether you have a base that's greater than 1 or less than 1. Okay? Now, recall that if your function is a logarithmic function of a particular base, then you're going to have one of these two basic graphs. It's either going to be logarithmic growth or logarithmic decay. Okay, yeah, so notice that the exponential functions have an infinite domain. They go on forever in both directions. The domain of this is from negative infinity to infinity. If you move things around, it doesn't change things. If you took this function and shifted it left or right or up or down, it goes on left or right forever, no matter what. You can change how far up or down it goes by changing the asymptote, but left and right, it's always going to have an infinite domain. Here, on the other hand, your function's domain is restricted. Just the basic logarithmic function, log base a of x, has a domain that is from 0 to infinity. Just like that. Okay, so what? Well, I can always change this domain by moving things left or right. If the asymptote moves, then the domain might start at -1 to infinity, or it might start at +7 to infinity. Okay, but so what? What does that have to do with this problem? Well, in previous examples, we looked at solving exponential equations. And you'll notice that every time that we checked our answer, it worked out. For checking these answers, all we were doing was plugging in the number to see if we got the same thing on both sides. And of course we did, because we didn't make any mistakes. That's because the exponential function has an infinite domain. That means any number that comes out as an answer, as long as you didn't make any mistakes, is a perfectly valid number, because any number can be plugged into an exponential function. A logarithmic function is different. Even if you did all the work correctly, it's possible that the answer you got is outside of the domain of your function. But if the answer is outside of the domain of your function, then it can't possibly be an answer. You can only have x values that are in the domain. So with logarithmic equations, when we check, we're not just checking to see if we didn't make any mistakes, we're actually checking to see if this is a valid solution. What we're doing is, just like back in chapters 1 and 2, we're looking to check for extraneous solutions. So for an exponential equation, you're checking because it's a good habit to make sure that you did everything correctly. For a logarithmic equation, it's not just a good idea, it's a required part of the problem. So here we're going to check for extraneous solutions. Now the nice thing about this is that we don't really have to go through all of the arithmetic. What do you mean we don't have to go through all the arithmetic? Well, we can. We can check to see if both sides are exactly equal to each other. However, sometimes that's going to be difficult to do because logarithms can lead you to some unpleasant numbers. Well, we don't really need to check the whole thing because look, all I really need to know is that the thing that I'm plugging in here is positive. If I take the log base a of something, that something better be positive. So when I check for extraneous solutions, what I'm really doing is I'm making sure that whatever is here is positive. If it's not, then that doesn't work as a solution. So here, well, that's what's inside my logarithm. And that's also inside my logarithm. So I don't have to check all of the arithmetic. All I have to do is make sure that these two are positive when I plug in this number. So here, if I take 5x minus 4 and I plug in 11 thirds, 5 times 11 thirds is 55 thirds. Minus 4. Well, 4, I can rewrite that as 12 over 3. I give those a common denominator. So 55 over 3 minus 12 over 3, and that is a positive number. That's, what would that be? 43 over 3. And that is positive. And that's all that matters, because if this is a positive number, that means this is a positive number. And I can take the logarithms of positive numbers. But now, maybe this one has a problem. So let's check that one. Let's take 2 times 11 thirds plus 7. Oh, and that's got to be positive, because 2 times 11 thirds, a positive times a positive is a positive. Here I can actually go through and say it's 22 thirds. But then I have a positive number plus another positive number, and that's definitely got to be a positive number. Here I'll go through the arithmetic, but I already know that it's going to be positive. I can write 7 as 21 thirds, and now I can add those together to give me 43 thirds. Oh, in fact, it's the same number. Well, yeah, we expect it to be the same number if we did everything correctly. So here, these numbers are both positive, which means that they work. These numbers are both positive, which means that by plugging in 11 thirds into these arguments, I don't fall outside of my domain. Let's look at another example. Let's say we have natural log. Natural log of x squared plus 7x is equal to the natural log of the number 18. Okay. Well, once again, we have two logarithms, same base. So the one-to-one property lets me just take the two arguments and set them equal to each other. And now I can solve that. This is a polynomial equation. I can go ahead and make one side equal to 0. So I can write this as x squared plus 7x minus 18 is equal to 0. I can factor that as x minus 2 times x plus 9 is equal to 0. And I have two solutions. If x minus 2 is equal to 0, then I get x equals to 2. If x plus 9 is equal to 0, I get x equals to minus 9. But again, I have to check these for extraneous solutions. Now you might think, oh look, that must be extraneous because it's negative. And you said don't plug in any negative numbers. Well, no, that's not what I said. What I said was, whatever number we plug in can't make these negative. So it's okay to have negative numbers as solutions. What we can't have is negative numbers in the argument. So let's go ahead and look at that. So this is a constant. I can't plug anything in there because there's nowhere to plug it in. So really, I'm just checking this one. So I'm going to take x squared plus 7x, and let me go ahead and plug in the number 2. If x is equal to 2, that's going to give me 2 squared plus 7 times 2. 2 squared is 4. 7 times 2 is 14. And that'll give me 18. All right, very nice. Let's see what happens if I plug in negative 9. Well, that's going to be negative 9 squared plus 7 times negative 9. Let's see, negative 9 squared is positive 81. 7 times negative 9 is negative 63. And if I subtract those, I get positive 18. So even though that's a negative number, even though negative 9 is the solution, when I plug it in, it gives me a positive, which is fine. So here, both of these numbers check out, and so both of these are solutions to my equation. So don't think you can't have negative solutions. What we're saying is when you take your solution and plug it into your argument, the argument should not be negative. The solution can be negative, and that's okay. But what if you can't use that one-to-one property, where this and this are equal to each other and we don't worry about the logarithms? Well, there's two cases where that's going to happen. The first one is the nicer of the two. Even though this one doesn't let you use the one-to-one property, it's still fairly nice and not super complicated. Let's consider an example, 5 times the log base 3 of, let's see, 7 minus 5x. And from that, we're going to go ahead and add 2, and that's going to equal to 17. My favorite number, 17. All right. So now, let's go ahead and see how this works. We would love to use the one-to-one property, but we can't because the one-to-one property requires you to have a logarithm on one side equal to a logarithm on the other side, and those logarithms should be in the same base. And that's definitely not what we have here. Okay, so for an example like this, what we want to do is we want to go ahead and start off by isolating the logarithm. There might be some other stuff around it. We don't want that other stuff around. We want this by itself so we can work on just that part. So now let's go ahead and subtract 2 from both sides, and that's gone. And that'll leave me 5 log base 3 of 7 minus 5x is equal to, well, let's see, that's just going to be 15. 17 minus 2. And now let's go ahead and divide by 5 on both sides, and I get my logarithm. So here I get log base 3 of 7 minus 5x equals to 3. Okay. So nothing that involves a logarithm has happened yet. Right now we're just getting rid of all the stuff around it. Subtract this and divide this away. Now, once you have a single logarithm by itself, if the other side also had a logarithm, we'd use the one-to-one property. But here you don't have a logarithm. So what you're going to do is you're going to use the inverse of the logarithm. Just like in a previous example with exponential functions, we can use logarithms to get rid of exponentials. We can use exponentials to get rid of logarithms. You say, well, how do you do that? Well, recall that if you take a base raised to the log base b of x, that just gives you x. This was part of the definition of a logarithmic function. It's the inverse of the exponential function. So if you have b raised to the log base b of x, that just gives you x again. You say, well, okay, I got the log base b of x part right here. I got the log of a base of a variable. Well, where is that going to come from? Well, we're going to put that in here. This process is called exponentiating. I love that word. It just sounds so dramatic, right? Exponentiating. When you exponentiate, you treat this not as its own separate expression, but you treat this as the power on some number. Whatever you do to one side of an equation, you do the same thing on the other side. So here we're going to say that's not the number 3, it's the power 3 on this number. That's not the expression log base 3, that's the power on this number. This process right here is called exponentiating. And it's one of my favorite words in all of math. Like I said, it just sounds so dramatic. Yeah? So now when we exponentiate, this property allows me to say, well, 3 to the log base 3 of that argument is just going to leave me that argument. It's just going to leave me the stuff in the parentheses. So 7 minus 5x. Here, that's just a number. 3 to the third power. 3 to the third means 3 times 3 times 3, which is 27. Just like that. And now things are nice. We can solve this. We can go ahead and add, we can subtract 7 from both sides. Let's subtract 7 here and here. And that'll give us negative 5x equals to 20. And now I can divide both sides by a negative 5 to get my result. So it gives me x equals to negative 4. Now remember, that might be the solution. Or maybe that's an extraneous solution. With a logarithmic equation, we don't have a choice but to check. So here we check for extraneous solutions. Assuming we've done everything right, that might not be our answer if, by plugging it in, it causes me a problem over there. So let's see what happens. So the only place I could plug something into is right here. So that's going to be 7 minus 5 times my x. Well, that's 7. Well, let's see here. 7 minus 5 times negative 4. That's 7 minus a negative 20. Double negative makes that a plus, which gives us a positive 27. So yeah, that's fine. Even though that's a negative number, plugging it in here gives me a positive argument. And notice you can even confirm all of the arithmetic. After all, log base 3 of, so that's going to be 27. So log base 3 of 27 is just the number 3. 3 times 5 is 15, plus 2 more is 17. So in fact, we can even confirm all of the arithmetic. But this is sufficient as long as everything else is correct. If you are confident that all of your steps are correct, all you really need to check for is if this gives you an undefined expression. All right, if you have a 0 or a negative in your argument. If you're not confident that you've done all of these steps correctly, then it's in your best interest to take this number and not just check it in here, but also check out the entire equation. All right, so go ahead and give this a try. Here's another example. Solve the equation. Log base 3 of y squared plus 6y minus 2 is equal to 1. Go ahead and pause the video. Give it a try, and once you've gotten your solutions, go ahead and restart the video. All right, so let's take a look. We're going to begin by isolating our logarithm. This is in the way. We want to deal with just the logarithm, so let's begin by just adding the 2 over to the other side. So that's gone. And this will leave me log base 3 of y squared plus 6y equals to the number 3. So now, to get rid of a log base 3, if we can't use the one-to-one property, we're going to exponentiate. So here I will use a base of 3, because that's a base of 3. If this was a base 5, I'd use a base 5. Make sure these bases are the same. Whatever I do to one side, I do on the other side. So now this will give me y squared plus 6y. This side, 3 to the third. 3 times 3 is 9. Times 3 more is 27. And now we have a nice polynomial equation. It's a quadratic. And we can go ahead and solve this by, let's go ahead and move one side so that it's 0 on that side. So let's subtract 27 there and there. Makes that go away. And we're left with y squared plus 6y minus 27 equals to 0. Now we can factor this. What two numbers multiply to give you negative 27 and add up to give you 6? Well, that must be 9 and negative 3. And so we have our solutions. Y plus 9 is equal to 0. That must mean y equals to negative 9. Whereas y minus 3 equals to 0, that must mean y equals to positive 3. But remember, those aren't guaranteed to work. We have to check these to make sure that that is a valid expression. So let's give this a try here. Let's substitute these numbers in and see what happens. So let me check for extraneous solutions. I didn't misspell the word check. I don't know what y'all were talking about. All right, let's plug the number 9 in here. Oh, sorry, that should be negative 9. So let's see here. Negative 9 quantity squared plus 6 times negative 9. All right, let's see. That's going to be, oh, my apologies. That should be in parentheses. So that's going to give us 81. 6 times negative 9, that's going to be negative 54. And if we subtract those, that's going to be 27. It's going to be 27. Okay, so that one's fine. If you plug negative 9 in there, that's perfectly valid. Right? It gives you a positive number, which a positive number in a logarithm is a perfectly acceptable thing. You just can't have 0 or negative. Okay, so that one works out. Let's try 3. 3 squared plus 6 times 3. All right, let's see. That's going to be 9 plus 18, which is 27. All right, so here that one, if you plug in the number 3, that also makes that positive, so everything's still good. All right, so that makes both of them correct, and so both of those are solutions. Now, for our last kind of example, let's take a look at something like this. You'll notice all of a sudden we have more than one logarithm. You say, well, yeah, that's very, very different from before. Before, we either had one logarithm on each side, or we had a single logarithm with other numbers around. But here, now I have more than one logarithm and numbers. So is that going to be different? The answer is yes, but only at first. Because remember, we have some properties of logarithms that allow us to take separate logarithms and combine them. So recall the process of condensing logarithmic equations, or logarithmic expressions anyway. When we condense, we can take, as long as these have the same base, we can take the log base b of x plus the log base b of y and write that as the log base b of x times y. And you can take log base b of x minus log base b of y, and you can write that as log base b of x over y. So here, if these are being added together, that's the first property. So instead of having them as two separate logarithms, I can merge them to write log base 2 of x times x minus 6, which is equal to 4. Multiply the two arguments together to form one new argument. Here, these can actually be multiplied, so let's write that as log base 2 of x squared minus 6x, not just distributed, x squared minus 6x and that's all equal to 4. And now this looks just like the last problem. So when you have multiple logarithms, it is going to be the same as this kind of problem, but you first need to take all your logarithms and condense them together to form a simpler problem. Once you have logarithm equals a number, or even better, logarithm equals another logarithm, then things are a lot simpler. So from here, we do the same thing we did before. I'm going to use an exponentiation using this base to simplify things out. Here, my base is 2, so I'm going to exponentiate with a base of 2. Whatever I do on one side, I do to the other side. And now, that's gone, and I'm left with x squared minus 6x. On the other side, 2 to the 4th power, well, let's see, 2 to the 4th is 2, times 2 is 4, times 2 more is 8, times 2 more is 16. All right, now we can solve that. Let's subtract the 16 over here to give us x squared minus 6x minus 16 is equal to 0. And now those can be factored. What two numbers multiply to give you negative 16 and add up to give you negative 6? Well, that's going to be minus 8 and plus 2. Just like that. So that means we have two solutions. If x minus 8 is equal to 0, then that suggests x is equal to positive 8. On the other hand, if x plus 2 is equal to 0, that suggests x is equal to negative 2. But again, we have to check these. All right, so let's see. We're going to plug in the number 8. Okay, well then that's going to be log base 2 of 8 plus log base 2 of 8 minus 6, and that's equal to 4. Well, that's all fine, right? Because here that's positive, and 8 minus 6, well, that's 2, and that's also positive. So that's okay. Log base 2 of 8 plus log base 2 of 2 is equal to 4. Now, if you're not confident that you've done these steps correctly, you could continue to simplify this to make sure both sides are equal to 4. But here, I'm going to assume that we're all confident in what we've done here, so we're just checking for our extraneous solutions. Okay, so 8 works out just fine. Let's try negative 2. Well, that's going to be log base 2 of negative 2, and right there I can stop. Because notice, if I plug in negative 2, that makes that argument negative. It's not about the fact that the number was negative. Look, I had a negative solution before. That's okay. The problem isn't that the solution is negative. The problem is that once you plug it in here, the stuff in the parentheses is negative. Look, it happens again. Log base 2 of negative 2 minus 6. Well, negative 2 minus 6, that would be negative 8. And again, you can't have a negative in a logarithm. The domain of logarithms is positive values. So here, this is extraneous. This one's thrown away. And so what does that mean? That means we have only one solution. Just like that. So for your last problem, go ahead and try an example. So we're going to take the log of x plus the log of x minus 10 is equal to the log of x minus 18. Notice it's the common log, which is base 10, but that doesn't really affect anything. After all, as long as the logs are all the same throughout, we won't have any major difficulties. All right, so go ahead and pause the video, give it a try, and once you are ready, go ahead and unpause and we'll go through it together. All right, so let's go through this together. You notice you have 3 different logarithms. Now, if we just had one logarithm on one side equals to the other logarithm on the other side, we could just use the one-to-one property. That's the nicest ones. Oh, but I don't just have one logarithm on one side. Oh, well, I could put these together and make it have one logarithm on one side. So I can go ahead and say log of x plus log of x minus 10. That comes together as log of x times x minus 10. And that's equal to log of x minus 18. All right, so now these multiply together, and that'll give me log of x squared minus 10x. Here I'm distributing. And that's equal to, well, let's see, well, nothing changes here yet. That's log of x minus 18. But now I can use the one-to-one property here, because I have the log of this equals to the log of that, which means that this must equal to that. So x squared minus 10x is equal to x minus 18. And this is our one-to-one property. If you prefer, you could even exponentiate. It would give you the same result. Here I could exponentiate with a base of 10. After all, that's what the common log is. It's base 10. If I exponentiate on the other side with a base of 10, hey, 10 to the log of x squared minus 10x, that's just x squared minus 10x. And here 10 to the common log of x minus 18 is just x minus 18. So you could use the one-to-one property, or you could exponentiate. Either one would be okay. So now we're left with a nice polynomial equation, or at least nice compared to what we started with. So now let's go ahead and check that out. We can go ahead and subtract the x here, and we can add the 18 there to make one side equal to 0. And that'll leave us x squared minus 10x minus another x is minus 11x plus my 18. And since all that's gone, that's just 0. This can be factored. What two numbers multiply to give you 18 and add up to give you negative 11? Well, that's going to be minus 9 and minus 2. And that's equal to 0. Okay. So then that gives me two solutions. X is equal to 9 and x is equal to positive 2. But again, these are just possible solutions. We have to check for extraneous solutions. All right, so let's try 9. Okay, well, that's going to be log of 9. Okay, well, that's good so far. Plus log of 9 minus 10 is equal to log of 9 minus 18. And you see that that's already not going to work. Because here, that's going to give me negative 1, and that's going to give me negative 9. So that's equal to log of 9 plus log of negative 1 equals to the log of negative 9. And since the way we define our logarithms does not allow for negative arguments, then that means that 9 is not a valid solution. So even though that's a positive number, that doesn't matter. When you plug it in here, these arguments become negative. So here that's extraneous. Let's try the number 2. And here we have log of 2. Well, that's okay. Plus log of 2 minus 10. And already you realize that's, well, that's not going to work for us. Same thing with 2 minus 18. That's not going to work. Because that'll give you log of 2 plus the log of minus 8 equals the log of minus 16. And since we only define logarithms for positive arguments, that means that 2 is not in the domain of this or this. And so these are both extraneous solutions. Now, is it possible to define logarithms of negatives? For those of you who stick with us for a lot longer, if you go with us past algebra, into trigonometry, and into calculus, when you get into further along into calculus, there are ways of defining logarithms with negative arguments. It does become a bit complicated. It has to do with imaginary numbers. So it's not that these can't be done, it's that there's not anything we can do with them right now. And so our functions are undefined for our purposes. So here, these are both extraneous. And so that means these are the only two possible solutions. Neither one works, which means this equation has no solutions. So that is the end of our section, and I hope you all have a nice day.